In this video, I want to take a look at the notion of a differentiable function. Remember back in Calc 1, we had the definition of a derivative. It was, the limit as h goes to 0 of blah, 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 whatever. The point being that if that limit existed, then we said the function has a derivative at whatever particular value of x you're looking at. And we said that made it differentiable at that point. The word differentiable was synonymous with has a derivative, right? And that was a point-by-point decision. That is, the absolute value function, for instance, is differentiable for most points, but at x equals 0, there's a problem, right? There isn't a single slope that you can say this is the slope. That limit didn't exist. Okay? So that was reasonably easy to define. If the derivative existed, it's differentiable. It's not so easy here with two or more variables. Okay. The problem is there are functions that have partial derivative with respect to x defined, partial derivative with respect to y defined. So slopes in those two directions are known, but not in other directions. That somehow something goes wrong in other directions. And what we mean by the slope in other directions we'll look at in future videos. But for now, let's just say something goes wrong. So the existence of the partial derivatives doesn't mean that the function is differentiable. Okay. So here's what our definition is. Right? We say that a function f of x is differentiable at a point x0, y0 if all points in some disk around P, so you got point P and then you got some little circle of points where this works. It might be a big circle, it might be a small circle, but it has to be at least some circle of points, some disk of points, that we can write this, that f of x equals f of x0, y0 plus the partial of f with respect to x at x0, y0 times x minus x0 plus the partial with respect to y at x0, y0 times y minus y0 plus e of x comma y when that error term e satisfies this limit. Now, I'll take a closer look at what this says. Notice the first part is f of x equals, the first three terms here are the linear approximation. Right? So we saw in the last video that the linear approximation approximates the function but doesn't get it perfect. Right? And the fact that it doesn't get it perfect means that there's some amount of error. So we're saying that we want to be able to write the function as the linear approximation plus some error function. And we want that error function to satisfy this limit. Now look at what this limit is. This is the limit as xy is getting close to 0, 0, sorry, not to 0, 0, but to x0, y0. And it's the error divided by the square root of x minus x0 squared plus y minus y0 squared. This is the distance away from x0, y0. So the point xy is some distance away from x0, y0. And you want to see how big that is and divide it into the error. So you're taking the error, which is the error in the z direction, divided by the horizontal distance that your xy point is from your x0, y0. So then how much vertical error for the difference horizontally in the known point and the unknown point. Okay? And if that gets small, if that limit goes to 0, then we say that the function is differentiable. Now notice, the denominator is going to 0. And so this denominator really wants this limit to be big, right? When you try to divide by 0, your answer is going to be big. So in order for this limit to be 0, not only does the error have to be going to 0, it has to be going 0 to 0 faster than xy is getting to x0, y0, right? That this distance is getting small because you're taking the limit as xy goes to x0, y0. So this is going to be getting small. This has to be getting real small in order for this to be 0. Okay? So if two things have to happen here, right? You have to be able to write it this way. And once you can write it this way, this error function has to be getting small fast as you approach x0, y0. Now, I've seen other definitions in other books where it didn't use this thing. Instead of the error function in this limit, they wrote this as, I've seen it as sort of like e1 times dx plus e2 times dy. and E1 and E2 have to be going to 0 as dx and dy are going to 0. Different ways, but I actually like this one. I think this is a very workable definition uh, to test for differentiability. Okay. So here's a picture of what's going on. Let's put this in 3D. Well, I guess it's still in 2D, but at least I can grab it, move it around, and let you see it better. So the yellow thing is my surface. This is the point that I'm going to say, I ask, is it differentiable? Okay. And so this is the x0, y0. That's in the xy plane, and then this is the point xy in the xy plane. So the function value at x0, y0 is this one, and the function value at xy is up here. Okay. Now the blue thing in there, this is always weird to move around, but the blue thing in there is the tangent plane at that point. Okay. So the linear approximation at xy is going to give you this z value right here. Okay. And the actual function value is way up here. So the difference, which is this multicolored little line segment, the difference is the error. Okay, so that e of xy, that error function, is measuring this length. Okay. So now, the other parts, whoa, are you dizzy yet? The other parts of that, come on now, let me see this. The parts of the expression that are the linear approximation is, this is the change in the y direction. And when I multiply that change in the y direction by the slope in the y direction, it gives me the change in z, right? Because of a change in y, you get a change in z, and that's this red height right here. Likewise, let's see if I can do this. In the x direction, there's a change, and because of that change, you get a change in z, which you calculate by the change in the x direction times the slope in the x direction, right? Rise over run times run is rise. And so this green bit here is the amount of change in the x direction. If you add those two together, which I think I do on the backside here, right? So there's the change in the y direction with its corresponding change in the z, and then the change in the x direction with its corresponding change in z. That's what you get for the linear approximation. Okay, so let's do it this way. Change in the y direction times the slope in y, change in the x direction times the slope in x, and you get the change based on the linear approximation. The error is what's left. Okay, and what we want to show is that when this change in y and that change in x get small, that this multicolored line segment gets way shorter than either of those two black line segments, right? That when you get down in close here, that this change, this error, is really, really small compared to those changes. Okay? If that's the case, then we say that we essentially say the tangent plane is a good approximation of the function, right? That error gets really small, and it's a differentiable function. Okay. This is actually an interesting point in that the idea of calculus and derivatives is that there are many, many functions out there that are very well approximated by a straight line. That is, the more you zoom in on them, the more they look like lines. It might have been really curvy function to begin with, but pick a point and zoom in, getting close enough, you can't tell the difference between it and a line. Right? Now, some functions certainly are not. Absolute value. I don't care how close you zoom into the point on an absolute value function, it's going to look like a point. Right? It will never look like a straight line because it's got a sharp corner there. But a sine curve, parabola, exponential curve, so many other curves, you zoom in, it will look straight. It is differentiable. It has a derivative. And in two variables, the idea is as you zoom in real close, it looks like a plane. If you have a cone, right, you got a cone, and the top of the cone is like an absolute value. You zoom in on it, it's never going to look like a plane. It's always going to look pointy. Right? But a paraboloid, a hyperboloid, all these other surfaces, that are nice and smooth. When you zoom in on them, they will look flat. They will look like planes. They're differentiable. Let's do an example and actually use that definition to show that a particular function is differentiable. So here's a, well, not too simple, but not too complicated function, f of xy equals x squared minus y. I'm just going to show at one particular point that it's differentiable. Right? Differentiability is a point-by-point thing. Right? That the example of a cone that I give is, it's not differentiable at the cone point, but it's differentiable everywhere else. Right? Just point by point, you decide, is it differentiable? So I'm just going to look at this 1 point, 1, 2. I happen to plug it into the function here. I need to know, I need to know two things. One, can I write this function in the way described? And then does the error function go to 0? So the answer is yes, this has a partial derivative. So the function value is -1. The partial derivative of x exists, and it's 2. The partial derivative of y with respect to y exists, and it's equal to, well, this is -1 always, so it's -1. So the linear approximation is this, and so yes, f of x, y could be equal to the linear function plus the error. So the error function is the difference between these two. And so there's the function, there's the linear approximation, subtract, and I get this, which is apparently a little bit off the page. Hang on a minute. Yeah, so the error function would be x squared minus 2x plus 1. Right? Just function minus the linear approximation is the error. Right? So I need to now look at, does that error function go to 0 fast enough? That is the limit as xy goes to 1, 2 of the error function divided by the square root of x minus 1 squared plus y minus 2 squared, is that equal to 0? Well, I don't know if this is a coincidence or not, but the top here happens to be a perfect square of x minus 1 squared. So there's x minus 1 squared. And then, this is one thing that I remember learning this kind of stuff that always bugged me. I liked equalities. Inequalities were kind of weird because it just seemed like you could do weird things. I'm going to add to the numerator y minus 2 squared. I mean, you might say, where did that come from? I'll show you where it came from. It came from right here. I just pulled it out of the air and I put it on the page. Right? Now, can I do that? Well, as long as I know what I'm doing and I deal with it appropriately. What I'm doing is I'm taking a fraction and I'm adding to the numerator of that fraction a positive number. Right? Also, I should say that I know that this fraction is already a positive number because the numerator is something squared, the denominator is the square root of something. Both of these are positive numbers. This is a positive number, a positive fraction, and I'm adding a positive number to the numerator of that fraction. That's going to make it bigger. Right? And so what I had before is smaller than, less than or equal to what I have now. Okay. So yes, I can just add it to it, but I'm not saying they're equal. I'm saying that this new thing I have is bigger than what I had before. Right? This is a less than or equal to sign. So the old thing is less than or equal to this new thing. However, this new thing, the bottom is just the square root of the top, so I end up with just the square root of the top. And if I take the limit of this, as xy goes to 1, 2, this is 0. And the limit that I wanted is less than this, and so, but it's all positive numbers, so it's a positive number that's less than or equal to 0. Well, it's a non-negative number less than or equal to 0, so it's 0. Okay? So this limit, in fact, is 0, and the function is differentiable at the point 1, 2. Now, here's an example or two where they're not differentiable. Right? Here's z equals the square root of the absolute value of x times y. Right? This has a partial derivative. So at 0, 0, this has a partial derivative with respect to x. It's equal to 0. It has a partial derivative with respect to y. It's equal to 0. Along the x-axis and the y-axis, right? If x is equal to 0, which would be the y-axis, or if y is equal to 0, which would be along the x-axis, the function value is 0. You multiply together, you get 0, you take the absolute value, you get 0, you take the square root, you get 0, it's 0. So along this axis, along that axis, the function is 0, and it's constant 0, so the partial derivative exists, it's equal to 0. However, in every other direction, weird things are going on, that this comes down really sharply and then goes back up again, right? Even at 0, heading off in different directions is odd. One way I see that this is not differentiable as well is the question of the tangent plane, right? Clearly, at the origin, sorry, this is differentiable in a lot of places, but at the origin, it's not differentiable. Look at the tangent plane. The tangent plane would be the xy plane. And so the question is the xy plane a good approximation to that function? Close to 0. Well, if you move away, let's say you go over to the point 1, 1, so you're a distance of radical 2 away from the origin. And of course, the function, the linear approximation would still be down here at 0, but the function's way up here at, well, if I plug 1 in there, 1, 1 in there, I'd be at 1. I'd have a height at 1. So the error between the linear approximation down here at 0 and the function value up here at 1 would be 1. And so 1 divided by the distance from the origin would be 1 over radical 2, right? And then get closer. The thing is that as you get closer, that ratio is always going to be 1 over radical 2. This is like an absolute value that's been squashed a little bit coming into the origin there. And so that limit is not going to be 0. I mean, if you came in along the x or the y-axis, you'd get 0 because the linear approximation is perfect along the x and the y-axis. But out here, it's really not good at all. So this is not differentiable at 0, 0. The linear approximation is not a good approximation. Okay. Another example here. This is square root of x squared minus y, sorry, not square root. So x squared minus y squared over the square root of the absolute value of x squared minus y squared. I have to throw these absolute values in because I don't want to take square roots of negatives. But what this function is essentially a cone cut. If you think of a full cone, it's got a top part and a bottom part. Cut it this way and then rotate part of that cone 90 degrees. So you've got part of a cone here and there, but then you've got the under part of the cone on this side and in the back there. Okay. This is a function that essentially looks like an absolute value in every direction at the origin. And I should say this is not continuous because it's not defined at the origin. If I plug a 0, 0 in, I got problems. But there is a limit as I go to the origin. It's 0. And so just consider that point at the origin filled in. So it is a continuous function once I fill the hole in and give it the function value 0. But so this is continuous here, but it's not differentiable because it doesn't even have a partial with respect to x and a partial with respect to y. If I move in the x direction here, right, the function comes like this and it goes down on the other side. It looks like an upside down absolute value, negative absolute value of x. So it looks like this, and at 0, there's a sharp corner. When you try to take the partial with respect to y, maybe I've got these backwards. This looks like y and that one's x, but it doesn't matter. It's also an absolute value kind of thing going up and down like that, and doesn't have a derivative at 0. So is this differentiable? Can I write the function as the linear approximation plus an error? Well, I can't even write the linear approximation because I don't have a partial with respect to x or a partial with respect to y. It just doesn't happen. I can't do this. So no, this is not differentiable at 0, 0. It is differentiable at most other points, not all points, because there's places where this gets completely vertical. So there's essentially the tangent plane is straight up and down, and that can't be written as a function of x and y. Right? There's multiple values of z for the same x and y values. So as long as you avoid those points and these points where it's vertical, it is differentiable in most of the other places. Okay, right? But not differentiable This one because the limit of e over the distance doesn't go to 0. This one because you can't even write it in the form that you're trying to write it to then find an error function. Just there's no linear approximation because the partial derivatives don't exist at 0. And before we're done with this video, I just want to point out two theorems. One is that if f is differentiable at x0, y0, then it must be continuous. This is the same as we had in Calc 1. A differentiable function is a continuous function. Not necessarily the other way around, right? The absolute value, or this function here, once you fill in the hole, that's continuous, but it's not differentiable. But differentiability implies continuity. And lastly, we saw in the example up here, I had partial with respect to x and partial with respect to y existing, but that didn't mean that this was differentiable, right? At 0, 0, both of them, both the partials exist, but it was not a differentiable function. Now, so I need a little bit more than just the partial derivatives existing to make it differentiable. If the partial derivatives exist and are continuous at x0, y0, then f is differentiable. Okay? So you need the partial derivatives to not only exist here, but they have to be continuous functions. So they have to exist in all points around it, and have values that are close to the ones you started with. Right? You can't have huge changes in those partial derivatives by just moving over a little bit. They have to be continuous partial derivatives. If they are, then the function is differentiable.